Okay, in this lesson I'm going to talk a little bit more about tree diagrams and the fundamental principle of counting. Okay, remember a tree diagram just displays the different outcomes of each task in a statistical experiment, and the fundamental principle of accounting just says the number of ways a statistical experiment can be completed is equal to the product of the number of ways each task can be completed. Okay, so box A contains 3 red beads and 4 blue beads. Box B contains 2 red beads and 3 blue beads. I want to complete a tree diagram for the following experiment. Choose a bead from box A and then choose a bead from box B. So task 1 is choose a bead from box A. Task 2 is to choose a bead from box B. Okay? Now box A contains 3 reds and 4 blues. Box B contains 2 reds and 3 blues. Other than that, I suppose these beads are pretty much identical. So really the number of ways that I can complete task 1, which is to choose a bead, even though there's 7 beads, if I'm just thinking about the colour of the beads, the number of ways I can complete task 1 is 2, and the number of ways I can complete task 2 will be 2. There's only really 2 colours, so there's only really 4 different possible outcomes here, if I'm only thinking about colours. Of course, if each of these beads had a different number on it, well, that would change that. There'd be 7 different ways to complete task 1 and 5 different ways to complete task 2, 35 ways. I probably wouldn't bother with a tree diagram that way. In that case, it would be too messy. So I'm just going to look at each task. Task 1 is to choose a bead from box A. I'm always starting with a point, and there are 2 ways to complete task 1. And those 2 ways, well, box A contains reds and blues, so I'm going to call the outcomes from task 1, which is to choose a bead from box A or in B, red and blue. Okay. The other thing I'm going to think about is the probabilities here. The probability of choosing a red from box A, well, there's 7 discs altogether, 3 reds in there, so there's a 3 in 7 chance of choosing a red from box A, and there's a 4 in 7 chance of choosing a blue from box A, so that's important also. Now I'm going to complete task 2. Notice there's only 2 branches so far, but when I put in the possible outcomes for task 2, you'll see we'll have 4 possible outcomes altogether. So completing task 2, which is to choose a bead from box B, well, even if I choose a red from A, that really doesn't have any effect on my possible outcomes from task 2, from choosing from box B. So choosing from box B, I could still choose a red or still choose a blue. If I chose a B from box A, well, my possible outcomes from box B are still red and blue. The other thing is to think about always is the probabilities. The probability of a red from box B, given a red from box A, well, actually what happened in box A has no effect on what's going to happen in box B. There's 5 discs in there, or 5 beads, I should say. So there's a 2 in 5 chance of getting a red, and there's a 3 in 5 chance of getting a blue, and that's going to be the same because what happens in box A has actually no effect on what happens in box B. Okay. So some things to think about. If I want to look at the sample space for this experiment, there are 4 possible outcomes. We have red, 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 blue, blue, red, or blue, blue. So there are my 4 possible outcomes when I complete this experiment. However, unlike our flipping a fair coin experiment, each of these 4 outcomes is not equally likely. If I looked at each of these, let's look at the probability that I select a red from box A and a red from box B. I'm going to write that as P of or. To calculate that probability, I'm just going to multiply the probability of a red from box A times the probability of a red from box B, given we got one already from box A. So 3/7 times 2/5. Okay, which will be 6/35. The probability of a red from box A, And the blue from box B is going to be 3/7 times, well, in this case it's 3/5, which would work out as 9/35. The probability of a blue from box A and then a red from box B is going to be 4/7 times 2/5, which would be 8/35. And then finally, the probability of a blue followed by a blue is going to be 4/7 times 3/5, which would be 12/35. This is a 12 in 35 chance that I'll get a blue followed by a blue. Okay. A couple of things to note: if I add up all those four probabilities, 6/35 plus 9/35 plus 8/35 plus 12/35, I will get 1. Because when I look at the probabilities of every outcome, I'm definitely going to get one of those outcomes, so the probability would have to be 1. Okay. If I wanted to calculate the probability of, say, at least one red, so the probability of at least one red. There's really two different ways to think about this. Well, we could say, well, at least one red, well, that could mean a red, or it could mean a red then a blue, or it could mean a blue then a red. And we can calculate that. So the probability of a red then a red, we said, was 6/35. Or, you know, we're thinking about plus here. These are mutually exclusive events. It's not going to be red and red-blue, so it's just a simple addition here. Plus 9/35. So there's a 6 in 35 of them will be red. 9 out of 35 of them will be red-blue. And then blue-red, well, 8 out of 35 of them will be blue-red. Okay, so that works out as 23 out of 35. There's a 23 in 35 chance of getting at least one red. Another way to think about that is the probability of at least one red. Well, all the probabilities have to add up to 1. So if I take away the one that has no reds in it, the blue, well, I should get the probability of at least one red. So we'd have 1 minus 12/35, which is 23/35. Another way to calculate the same thing. Okay, so tree diagram, it just displays all the different outcomes from each different task. Sample space contains all possible outcomes from an experiment, and then we can calculate probabilities. With tree diagrams, do include the probabilities. You see them written without. When you know them, sometimes they're not obvious, okay? Or sometimes we need to do a bit of research to figure out these. But in this case, beads in a box, it's not so complicated. Okay, let me look at a slightly different experiment where maybe the events are not independent. So a box contains 5 yellow beads and 7 green. I want to complete a tree diagram for the following experiment. Choose 2 beads. So the two tasks are choose a bead and then choose another bead. Task 1, choose a bead. Task 2, choose a bead. If I'm only interested in color, well, there's only 2 ways to complete task 1, and there's only 2 ways to complete task 2. The ways to complete task 1 are yellow or green, and the same for task 2. So there should be 4 different outcomes in this experiment, and you'll see that from the tree diagram. In this case, I might do it vertically. I did the last one kind of horizontally moving across. Let's do this one vertically. It doesn't matter, pick your preferred method. Always starting from a point. There are 2 tasks. Task 1 is to choose a bead, and there are 2 possible outcomes when I do that. They're called yellow or green. And the probability that I will select a yellow, well, there's 5 yellow and 7 green, so there's a 5 in 12 chance that I'll select a yellow, and there's a 7 in 12 chance that I will select a green. So 5 and 12, 7 and 12. Notice they add up to 1. Task 2, is to select another bead, and the possible outcomes are still yellow and green. If I've chosen yellow on the first one, I can still choose a yellow or green on the second one. If I've chosen a green on the first one, I can still choose either a yellow or green on the second. Now we have to think a little bit about the probabilities here, because if I've chosen a yellow on the first one, well, that changes things, because if given that I've chosen a yellow on the first one, that'll mean there's only 4 yellows left in there. So there's going to be 4 out of it, and there's only going to be a total of 4 plus 7, 11. There's still 7 greens in there out of the 11. Notice the sum of 4 and 11 and 7 11s is 1. So the probabilities change. These events are not independent. What happened in the first task of the experiment will affect what happens in the second task. If I'm going to look at the probability of yellow, given that it was green in the first, well, given that I've taken a green in the first, that leaves only 6 greens. So there's 11 beads in there now. If I've taken a green on the first one, 5 out of those 11 will be yellow, and 6 out of those 11 will be green, because we've reduced the number of greens by 1 and the total number of coins by 1. And again, think about the sample space. If I want to look at the sample space for this experiment, we've got yellow, 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 green, green, yellow. Oh, let me just fix that. Green, yellow. Board is misbehaving. Again. So green, yellow, and then finally green, green. And I can work out the probabilities of each of those. The probability of a yellow and then a yellow. The probability of a yellow and then another yellow is the probability of a yellow on the first, 5 12s, times the probability of a yellow on the second, 4 over 11. So we get 5 over 4 times 12 over 11. Bit of a cancellation here might be nice. So 4 goes in there once, in there 3 times. So we can get 5 over 33. Probability of yellow, green. Well, yellow on the first, 5 12ths. Times the probability of a green on the second, given a yellow on the first. That's 7 over 11. Okay. No great cancellation there. 5 7s, 35. 12 11s, 132. 35 over 132. Notice they are not equally likely outcomes. Probability of a green and then a yellow is the probability of a green on the first, which is 5 over 12 from your tree diagram there. So probability of green on the first is not 5 over 12, it's 7 over 12. Probability of green on the first is 7 over 12. Times the probability of a yellow on the second, given a green on the first, which is 5 over 11. Okay, note that's actually going to be the same as the previous one, 35 over 132. And then finally, probability of a green followed by a green is going to be the probability of a green on the first, which is 7 out of 12, multiplied by the probability of a green on the second, given that we got a green on the first, that's going to be 6 over 11. There is a bit of cancellation in here. There's 6 in there once, in there twice. So we're getting 7 over 22. And I guarantee if you add up those 4 fractions, you'll get 1. Each of these pairs add up to 1. All 4 of these final ones add up to 1. So you can work out probabilities from your tree diagram. Okay, so remember, tree diagram is just a way of showing all the possible outcomes from each task in the experiment. And the fundamental principle of counting says to find the number of ways an experiment can be completed, we just take the products of the number of ways each task can be completed. in this case 2 by 2, 4 ways. Yellow, 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 green, green, yellow, green, green. Okay, so practice, practice, practice.